So today we're going to be looking at using Lewis dots to determine molecular structure. To determine molecular structure. In other words, if you know a formula, how do the atoms connect? How do they make their molecules? So for this, there's a goal. The goal, and it's the goal for the atoms, is that most atoms are stable with 8 valence electrons. And this is really important, 8 valence electrons. Now, most of them don't start out with 8 valence electrons. They start out with 6 or 5. So in order to get their 8 valence electrons, they share with another atom. And this is called the octet rule. Now, before we go on further, there are 3 exceptions. So we're going to say the 3 exceptions. These are atoms that are too small to have 8 valence electrons around them. They don't have enough protons in them. And the first one is hydrogen. Hydrogen is stable. Well, it starts out with 1 valence electron, but if it can just find a match for that, it's perfectly stable with a total of 2 valence electrons. So hydrogen's the littlest, and on the periodic table, you know, hydrogen's way down there. The next one over is helium. Helium does not form bonds, so helium doesn't get any valence electrons, so we'll skip that. Lithium is always ionic bonds, it never shares, but beryllium and boron, they're little atoms, but they do make covalent bonds, but they can't handle 8. So beryllium starts out with 2 valence electrons. If it can just find partners with those, it's great. So it's stable with 4 total valence electrons after it makes its bonds. And then boron starts out with 3, but if it can just find partners for those, it's good. So it's happy, it's stable with 6 valence electrons when it's all done. All the rest, all the other atoms that make covalent bonds are stable with 8. So in forming the bonds that they make, they all need to end up with 8 valence electrons. So the idea is that we want to find some combination, some connection with them, so that they'll all have the valence electrons that they want. And here's the system. This is what Gilbert Lewis came up with. So Gilbert Lewis's system. He just invented it so that people could understand the final structure. It doesn't really show what atoms look like. It's just a sort of a shortcut for it. And there are 5 steps. 5 steps. We're going to take, for example, carbon tetrachloride, CCl4, 1 carbon, 4 chlorines. How do they connect? So the first step, and I'm going to put a box for the first step, is to count up all the valence electrons that these atoms bring to the molecule. Of all the valence electrons the atoms bring. So for carbon tetrachloride, we need our periodic table to figure out how many each of them have. Carbon is in group 14, which means carbon has 4 valence electrons to start. Chlorine is in group 17, so we've got 4 of these, and each of them have 7 valence electrons. So we count those all up and add them up. They add up to 32 valence electrons. Now we're going to put that number totally aside. We'll come back to it. But we don't pay attention to how many they start with from now on. Okay, second step is put a singleton in the middle. So you're going to figure out which one is the singleton. There's not always a singleton, but often there is. Singleton just means there's one of that kind of atom. So carbon, there's one carbon, 4 chlorines, carbon is the singleton. So we figured out that carbon was the singleton. And then we're going to connect the other atoms to the singleton with single bonds. So the other atoms to the singleton with single bonds. So here we'll put carbon there and put chlorines all around it. Now you think in terms of a box, so there's a top and a bottom, a left and a right. We put them around there. Okay, then, just out of the air, not even paying attention to who started with what, you give all atoms the valence electrons they need. So here's what I mean by that. If we look at carbon, carbon is forming 4 bonds. Each one of these lines represents 2 shared electrons. That's what a bond is 2 shared electrons. So carbon, in its sphere of influence, around it has 2, 4, 6, 8. It's got its 8 valence electrons. That's stable for carbon, so carbon is fine. We don't need to put any more dots around carbon. Chlorine, on the other hand, needs 8, but it only has 2 because it's only forming 1 bond. So chlorine needs 6 more valence electrons. And to show those, we put dots in pairs on top, bottom, left, right, whatever needs it. So if I put 3 pairs of dots, so 6 electrons, I've got 2, 4, 6, 8. Now this chlorine has its stable octet. It's good. We'll do that to the rest of the chlorines as well. So we might be done, but to see if we're done, there's one last step. And that 5th step is to count up. We're going to count up all of these electrons and see if it adds up to 32. So count up all the valence electrons to see if they agree with the first number. With the number, let's say, from step 1. So here we go, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And I like to write that number down here just so that I can have it written somewhere. And then I check, and sure enough, 32 was the same as 32. So now this carbon tetrachloride is done. So let's just do a few examples using that system. Let's say, for example, we wanted to do NH3, ammonia. First step, got to have a periodic table. We find nitrogen is in group 15, so it has 5 valence electrons. Hydrogen is in group 1, so each hydrogen has 1 valence electron, but there's 3 hydrogens, so I'm going to say 3 hydrogens have a total of 3 valence electrons, so it adds up to 8. Now I set that aside and try the structure. Look for a singleton. Nitrogen's a singleton, so that'll go in the middle. Bond the 3 hydrogens to that with single bonds. Check to see if everybody has what they need. And if you remember back here, we said that hydrogen just needs 2 valence electrons. Here's our notes from that. So hydrogen was stable with 2. So right now, put that there. This hydrogen has 2 valence electrons because of the 2 shared electrons. So I don't need to add any dots to hydrogen. This is always true for hydrogen. It always makes 1 bond. But nitrogen needs 8. So we'll give it, it already has 2, 4, 6. We'll give it 2 more for its 8. So hydrogen has, and this is called a lone pair of electrons. And sometimes it's called an unshared pair. So now we count up 2, 4, 6, 8, and sure enough, that works with that. Now, what if we had a charged particle? Let's say that we have, for example, NH4 plus. So here's another example. Instead of NH3, we had NH4 plus. What do you do with the +1 charge? Well, let's try. Nitrogen, we already saw, has 5 valence electrons. Now we have 4 hydrogens, so that's a total of 4. But now the plus sign means that it's lost 1 electron. That joke, if you lose an electron, you're positive. Are you sure? I'm positive. Yeah, so if you lose 1 electron, you have a +1 charge. That means you just take 1 electron away. So that means it has a total of 8. So we'll put the singleton in the middle, put the hydrogens, now there's 4 of them all around. Check to make sure everybody has what they need. Hydrogen needs 2, has 2. All of the hydrogens have 2. Now this nitrogen has 2, 4, 6, 8. That's nice, so it's done. But to show the positive charge, you need square brackets and either a plus sign or a +1 sign. So this had 8, and that was right. So here's another example. Let's say we have the chlorate ion, ClO3 -1. So we'll do the same thing. Chlorine is in group 17, so it has 7 valence electrons. Now oxygen is over here, it's in group 16, so it has 6 valence electrons. We've got 3 of them, so 3 oxygens have 6 each, so that's a total of 18. But now it has a -1 charge, and the -1 means that it's gained an extra electron. So extra electron, and we'll say that's the -1 charge, means that we have an extra electron. So we add 1 electron in there. So now we have a total of 26 for this. So we take a look. There's a singleton. Chlorine is a singleton. That'll go in the middle. We've got oxygens all around. And then there's just the 3. Now we have to satisfy the octet rule for everything, and nothing is complete here. Let's start with chlorine. Chlorine has 2, 4, 6. It needs 2 more. So now chlorine's good. Each oxygen only has 2. It needs 6 more, so it has a total of 8. All right, now we've got the singleton in the middle, single bonds everywhere, and we've got every atom has its stable octet. So now let's count up and see if it adds to 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We're good. So we're done, except we need to put square brackets on it because it's an ion, and then put the -1 charge. So anytime your structure is really a polyatomic ion, you need the square brackets. So for all 3 of these, the number that we've counted up has added up to the same as the original number. What if it doesn't? So here's when things go wrong. We'll take a look at one of the most important molecules there is, oxygen. So you say, okay, I can do this. 2 oxygens. Oxygen is in group 16, so each one has 6, so that's a total of 12 electrons. You think this is going to be so easy. So we say, we only have 2. The only thing you can do is bond them with a single bond. Now we give everybody the electrons they need. So now each oxygen has 8 valence electrons around it. 2, 4, 6, 8, and 2, 4, 6, 8. So now we count up and see that it adds up to 12. 2, 4, 6, 8, 10, 12, 14, but it doesn't. So this is not quite it. What you do when there's too many electrons in your structure with single bonds, you do a double bond. So try a double bond. So we're going to say, instead of a single bond between the 2 oxygens, there's a double. What that means is that they're sharing 2 pairs of electrons. So now this oxygen already has 4 electrons from the double bond. So it only needs 4 more. And to show those 4 more, you keep them as pairs. So now this one has 2, 4, 6, 8. Now we need to do the same with the other oxygen. 2, 4, 6, 8, 2, 4, 6, 8. So now we count up the total 2, 4, 6, 8, 10, 12. And that's right. So this one up here was not right. That one had too many electrons. This one now, each oxygen has its 8 valence electrons, and the total adds up to the valence electrons that the oxygens brought to the bond in the first place. So that's why you count in the first place, is to figure out if you need a double or a triple bond. Let's take a look at a triple bond. Nitrogen is the other very important gas that's in the atmosphere. Your atmospheric composition is about 78% nitrogen and about 20% oxygen. So these are both really common, very important kinds of molecules. So nitrogen is in group 15, so it has 5 valence electrons. 2 nitrogens then are going to have a total of 10 valence electrons. So you say, okay, bond with a single bond, and let's say we hadn't just done oxygen, so you don't know exactly where this is going. So you try single bonds. 2, 4, 6, 8, 10, 12, 14. Not going to work, right? So we know that's not good. So we need to get down to 10. Let's try a double bond. You can see where this is going. Give each atom its 8 valence electrons. 2, 4, 6, 8, 2, 4, 6, 8. So total 2, 4, 6, 8, 10, 12. Just like with the oxygen, that's not enough. So we need to go one more. We'll try a triple bond. Triple bonds are rare, but if you need them, you need them. So this nitrogen now has 6 electrons in its sphere of influence. It just needs 2 more. And this nitrogen, same thing, has 6 from the triple bond, needs 2 more. Now we'll count it up. 2, 4, 6, 8, 10. And it's just right. So nitrogen has a triple bond. What we've seen is that if there are 2 too many electrons, 14 instead of 12, then you can do a double bond. If there's 4 too many electrons, from 14 to 10, then a triple bond works. Turns out that 2 double bonds would also work for that. All right, there's just a couple of other small ideas in this little unit that I want to take a look at. And one is called resonance. Resonance structures. Resonance structures happen when you need a double bond, but you can't decide which side to put it on. So let's take, for example, if I had NO2 minus 1, that's the nitrite ion. When you add them up, nitrogen is in group 15, so it has 5 valence electrons. You've got 2 oxygens. They're in group 16, so they have 6, so a total of 12. We have an extra, because it's a minus 1 charge, so we'll add 1 electron. So we have a total of 18. And if we put the singleton in the middle, like we should, and bond them all with single bonds, and then give everybody the electrons they need to have their 8 electrons, and then we count them up, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, we have 2 too many. But the question is, which side do you put it on, the left or the right? And what they have found to show this, that the best way to show it is to write both structures. So we'll write it with a double bond on the right, and we'll write it with a double bond on the left. So if this oxygen has 1 from the bond, we need to give it 6 more. So now this one has 2, 4, 6, 8. This nitrogen, it's kind of odd, but it's got 2 on one side, 1 on the other. So 2, 4, 6, it already has 6 electrons because of the way the bonds are. So it needs 2 more. So now this nitrogen has 2, 4, 6, 8. That's good. Now this oxygen has 2, 4, so it needs 4 more, and we'll keep them together. So that's one of the 2 possible structures, and we'll give it its minus 1 charge. But you also write the other possibility with the bond on the other side, and then give it all the dots that it needs, and the square brackets because it's a polyatomic ion, and you write a little double arrow in between. What this double arrow means is, what they've found is that really this double bond is switching back and forth between both sides super fast, so that any machines that are measuring the bonds in here don't find a double bond or a single bond. They just find 1.5 bonds. So it's resonating back and forth, just like when you pluck the string of a guitar, it wiggles, it vibrates back and forth. The electrons that make that extra double bond are going back and forth. So that's a resonance structure. The other idea are called isomers. And these are atoms of the same chemical formula that have totally different structures. And I'd like to show, for example, C2H6O. There's 2 possible ways to write this molecule. Actually, there's probably more than that, but there's 2 that are really common. And one of them has this particular structure. It's got CH3, which is called a methyl group, and then carbon, another carbon, so there's the second carbon, and then an oxygen, and then a hydrogen. And to have everybody have their stable octet, we need a couple dots for that oxygen, a couple lone pairs. So this is called ethyl alcohol. And it has a certain smell to it. It has certain characteristics, boils at a certain temperature. It's found in beer and wine. It doesn't kill you if you smell it, and the body can handle some of it. But you could also write this in another way. You could write it with a methyl group, and then the oxygen, and then another methyl group. Still C2H6O. Both of them have the same formula. But this is totally different. This is dimethyl ether. And it's an ether. They use ethers as anesthetics. You breathe in ethers and you pass out. So you breathe in a little ethyl alcohol, you think it smells like markers, you breathe in some of this and you're on the floor. Totally different molecules, different boiling points, different characteristics. Same exact chemical formula. So these are isomers of each other. Same but different. And to label these as a bottle, if you're labeling a bottle on the shelf, you would never write C2H6O because you wouldn't know which one you had. So instead what they do is they have the formula copy the structure. So they would write C2H5OH, C2H5, and shows the OH at the end. This one, on the other hand, they would show CH3O, CH3, because you have CH3 and then an oxygen and then the CH3. And ethers, yes, they have lots of puns that go with it, and people do talk about the ether bunny, and they say that the little oxygen in the middle is like the hole that the ether bunny goes down, and it works beautifully. So Lewis structures, very, very handy. They work great, but they don't show the 3-dimensional shape. They just show the 2-dimensional probable structure of a molecule. And we'll see the 3-dimensional shape in the next little video.